So basically what regression does is that it gives you an idea of how you are going to determine the movement in one variable based on movement in another or a set of variables. And we have different names for them. The ones that are very intuitive is that the response variable and the dependent variable. So if it's a response, it means it's responding to another variable, which is the independent or the explanatory variable. And we have to note at this point that regression and correlation are no causality implications. If we want to determine causality, we need to use specific causality methods for that. So it's only about relationships. One does not distinguish between the nature of the variables, but the regression does distinguish between the nature of the variables. So that's what we want to look at briefly. Regression, again, the one we are looking at, we may be looking at the linear one, but we'll move forward to the linear, non-linear relation. So we can have a dependent variable, or that's a time series or a cross section, or a combination of the two, which is panel. We can have dependent variable, have some intercept and y, plus of course term that is capturing all the other terms which cannot be determined by x. So this is simple linear regression because we have only one dependent variable and one independent variable. But we can expand this to, let's say, a vector of xi onto k plus I. So if I have a number of independent variables which we represented by xi, and a sum of them, so that is multiple linear regression. And as always, if we, for some reason, the exponents of the variables change from one to something else, then we move from a linear regression to a non-linear regression. Because some of the representations are there. So this is the, if you like, the classical linear regression equation. And one thing you need to know about linear relationship or the classical regression relationship is that it is parametric. And when it's parametric, there are a lot of conditions that have to be met before we are able to use the model for any useful thing. Okay. So we know how we need to talk about how we need to use this relationship. So again, we have our dependent variable here, set of independent variables, including our residual term, which captures all other independent variables that we do not even have data for, or we do not even know them. So all other variables that can determine y, but we don't know how to quantify them. So you see that there are three parts of the model, 2 and 3. And for a parametric model, it means that the assumptions are going to be on the parts of the model. So if you are diagnosing the model and subsequently, as we will do, we need to go across those three portions of the model to diagnose. Now we said that this model, let me use a blank slide to show you something. This model is describing the evolution of the relationship between two variables or more variables. So if you remember our scatter plot, was like this. Let's assume a direct relationship. So we have our x and we have our y. Now this relationship is there. We may perceive that it's direct and maybe somewhere strongly related. So what we do not know is how the relationship actually evolves. what percentage of changes in y is corresponding with changes in x. So to do that, we need to have straight line going through the regression, the scatter plots. So we may have, say, line 1 and line 2 and another line 3 for illustration purposes. So if we need to describe the relationship between x and y, which of the 3 lines do you think will be the best one to describe the relationship between x and y? So basically, the regression line, the straight line, is a mean regression. Mean is the center, right? So if you are doing this manually, if you have a small data points, one of the ways to find the mean of x and y, plot that point, find the values that are less than each one of the means. You find the mean of them, you plot them as well. And those that are more, you plot them. And you can have about 3 points and you join the lines. Now, so what is happening is that, as I'm not sure of the name, so if you take a point here, any vertical point between L3 and any distance between L3 and a point, as well as any distance between L1 and L2 and a point, what you realize is that the distance between L3 and the points are smaller. Okay? They are smaller than for the rest. And that is very important because that will satisfy the fact that the line is going through the most of the points and the line is going through the center. So basically what is happening is that you have your regression is basically y equal to beta naught plus beta x plus the error term. So you're going to have y minus beta naught plus beta 1x got your error term. And those are, we are going through the center, the sum, the difference between each of them should be equal to 0. But you don't want to make 0 because we need to continue to make our further statistics. So you want to square them just as you do when you are looking for standard deviation. And when you square, you also want to add them. So sum of the squares between the dependent variable and the independent variable. And if it's for L3, you realize that this sum will be the least as compared to L1 and L2. So you have sum of least, the least of the sum of the squares of the errors, which is the difference between the regressor and the regressor. And that's basically the ordinary least squares approach to regression. So that's actually an estimator to the relationship you want to find. The other estimators, like the maximum likelihood estimator, which we are not looking at, but we are looking at the ordinary least squares. So you have the least is the minimum, the squares is the difference between the x and the regressor, which is the residual. So basically that's what the relationship is about, and that's what is being described here in these slides. If I show you this plot, that is another description of that relationship. Okay, so let's go back to one more thing here. If I write dx, so dy over dx, this is total, if you like, differentiation or total derivative. But this is partial derivative. Partial means, if you remember the partial correlation we did, we're keeping some variable constant, and the representation here is the partial relation. So we are looking at the changes in y that can be explained by a change in a particular x, keeping all the other x constant. But if you come to this one, for example, So let's say this is 2 and this is 1. If you come to this, we are not keeping any variable constant, so it's not partial. And that's how you interpret your correlation coefficients. The changes in y that can be attributed to a particular change in x, given that all other x values or independent variables are held constant. If you are not able to do that, then there's a contemporaneous influence of one variable against over the other. So that's how we look at our relationships. One thing that we have to check here, we have to stay here, we realize the mean of this error term was going to be 0 because it's going through the center. That's one key assumption or condition for the regression equation. Because it's going through, if it's linear and if it's normally distributed, the line should go through the typical center, and the difference between the lower side and the upper side is going to cancel out, and that will be 0. And that's a key condition. If that is not satisfied amongst all the other conditions, that's a problem. We have to find another regression approach to do the work. So what are some of the assumptions? Let's look at them before we add other things. So the regression has a lot of assumptions. One of them is a linear relationship, which we have established now. The mean of the residual should be 0. We just looked at that one. And the fact that we have deterministic regressors. What it means is that the independent variables, the data for them are not stochastic, they are not random. If you have a typical data as we use, the data that we are going to use are known at the time that we are making an estimation. They are not based on a random variable, unlike typical random modeling where each variable is not known for certainty, but these ones are known for certainty. Now, also, if the data is normal, the data is based on normal distribution, then the residuals should have a constant variance. If you look at this, it's going through the center. The variance at this point, if you compare them, it will be the same. So it has to be constant. Another thing is that, where is the other one? If it's for a time series, then they shouldn't be dependent on each other. Because one of the relationship, the conditions for the residual is that they are independent of each other. They are purely random for the residual, so they are random. Or if you like, it's a white noise. That means they cannot be dependent on each other. If they are also random, which it means that they cannot be they cannot relate with any of the independent variables. If that happens, there's a problem. There's an endogeneity issue. We captured this one as well. There should be some condition of relationship between the independent variables and the dependent variable, which is our precursor to the regression. So our correlation should not be 0. And then the model specification should be correct. Are you specifying a linear model to the relationship, or you are specifying a nonlinear model? Okay, that should be very clear. And for you to use your model, a typical regression model is a predictor. And if we push it, we can use it for forecasting. That means we are using it for decision making. Now, for a model to be used as a decision-making tool, it has to be good enough. And you can do that by diagnosing the model. If you diagnose the model and it fits well, remember at the early stage, you said quantitative decision-making is about describing a relation, a problem based on a theory or the data. You specify the model, you find data that you can use, and you estimate the model. And you diagnose the model if it's good. If it's not good, you have to refit or adjust the model. So for regression, that's the same thing. You have to diagnose the model across all these assumptions. Then you can use the model for the purpose for which it was built.